Today we'll discuss an essential service of TCP known as flow control. Any implementation of TCP should invariably contain this particular aspect. First, we'll see what flow control is, and then we'll see how this is achieved in TCP. Let us look back and see what are the different header fields which we have discussed. All the fields with a tick mark this we have discussed in our previous lectures. Today we'll discuss this particular header field known as receive window. This particular header field receive window is used for TCP flow control. So TCP flow control is basically a matchmaking service. It matches two things. It matches the rate at which the sender is sending data against the rate at which the receiving application is reading data. That means we have a sending side, we have a receiving side. So what TCP flow control does is it matches the rate at which the sender is sending data and the rate at which the application in this receiver is reading data. Be clear about this subtle difference. It is not the matching between sender rate and receiver's rate. It is a matching between sender's rate and the rate at which the application at the receiver's end is reading data. Let's try to understand it more clearly. Till now we have been saying that the sender sends data to the other end. Till now we have not spoken about at what rate does the sender sends data. We simply assume that data comes from the application layer, it makes packet, and these packets are delivered to the other end, and depending on the acknowledgement, the sender will retransmit packets which are lost. Now, at what rate does the sender send data? Does it send data at the full rate? Say it has a transmission rate available of 1 Gbps. Does it send data at the rate of 1 Gbps? Say the data comes from the application layer and 5000 packets are created. Now, after the TCP connection is established, and if the transmission rate allows to transmit data at a very fast rate, does the sender send all the 5000 packets one after another immediately after the connection is established? If it is allowed to, say if the transmission rate is high and is capable of, does it send all this packet one after another immediately without bothering if something is happening in the network or whether the receiver is capable of handling that amount of data? So this particular aspect we have not discussed till now. Now, if the sender sends data at full rate without any consideration, if everything is fine, then it's okay. But certain drawbacks may happen if the sender decides to send data at the full rate from the very beginning. Now, it may happen that there is a congestion in the network. What does congestion indicate? Congestion indicate that there is a very high traffic. A high amount of data packets are there in the network. That means many nodes are being active. They are all sending packets. So a huge number of packets are there in the network. Now, when there is a high traffic, and now if the sender starts sending data at a very high rate, a huge number of packets, obviously it will aid in that traffic. That means the traffic will increase more. Now, when the traffic increases more, this will result in packet loss. This we have already discussed. If a huge number of data packets are there in the network, the intermediate routers will be unable to handle all the data packets in its limited amount of buffers, and due to that, packet loss will happen. Now, this situation is known as congestion. So one aspect is this: if the sender starts sending data at its full rate without bothering what is happening in the network, it may happen that due to the conditions in the network, traffic congestion happens. Now, this should not happen, obviously. And this aspect where traffic is maintained, where congestion is maintained, this particular aspect is known as congestion control. This we will discuss in a separate lecture. Now, the other aspect is, say the receiver is sending data at its full rate, say at a rate of 1 Gbps. Now, what happens if the other end, the receiver end, is not capable of handling those packets at the same rate? So your data is flowing from this sender to this receiver. We have already discussed that It is not something like that the packet arrive and the packet is immediately delivered to the application layer at the other end. We have already seen that this side maintains a buffer. So the packets are first stored in the buffer, and a certain duration of time a number of packets are delivered to the application layer. So say it is sending packets one after another, and say after the buffer stores around 50 packets, these packets are cleared and sent to the application layer. Clear? This we have already seen. Now say if this sender is sending data at the rate of 1 Gbps, and the data is coming to this buffer, and if at the other end the application layer is reading data at the rate of, say, at much lower, let's say 500 Mbps, what will happen? The rate at which data is being sent and the rate at which the data is taken from the buffer is not same. And what will happen? After some time, this buffer will overflow, and when this buffer will overflow, obviously packet loss will take place. And packet loss is a big business. If there is a packet loss, the sender has to again retransmit those packets. Those retransmission may again aid in congestion or something like that. So it is always beneficial that retransmission does not happen. So now our essential task is that this sending rate and the reading rate should match. They should be matching such that the rate at which data is being sent and the rate at which the data is being consumed by the application at the other end, they should ideally be equal. Now how to achieve this? And this is the task of TCP flow control. Clear? Now this TCP flow control is receiver centric. That means the sender should send data at the rate at which the receiver is capable of handling that data. Clear? So it is not that the sender sends data at its full rate. It should consider the receiver also. The rate at which the receiver application can handle, that is the rate at which the TCP sender side should send data. So the basic aspect of flow control should be clear. Now we'll see how this is achieved. Now we have seen that the receiver side maintains a buffer. So assume that this is the buffer. This we have already seen. So this is the data buffer. So the data is coming from the network layer, and these packets are being filled in this buffer, and the application process is reading this data time to time. So there will be a spare room available for data, and it should not happen that data should overflow this spare space. That means the rate at which the sender is sending data should not be such that this spare space is overflown. If it does happen, then obviously there would be packet loss. Now let us look at the states of the sender as well as the receiver. Let's look at the receiver side. So from the receiver's perspective, these four states may happen regarding the data it has received. So it might have received some amount of data which it has given to the application. So the other side is sending data packets. It has received some of the data and which it has already given to the application layer. Now it might have received some data which it has also acknowledged, but it has not been given to the application layer. So this is the part which is buffered. So that means data has started to come from this sender side. Now say some data was buffered, and then after some amount of time the data was sent to the application layer. So this is this part, received and given to the application. Now some data may be in this buffer. They have been acknowledged, but they have not been sent to the application layer. So these are buffered. Now it's also it may happen that some data has been received, but it has not been yet acknowledged. That means some data it has received, it is in the buffer, but they have not been acknowledged. And there may be some data in the pipeline. That means the sender has sent some data, but it has not yet been received at the receiver's end, and they are in the pipeline, so they are not yet received. So this is the status of data from the receiver's perspective. data which has arrived and already given to the application, data which has arrived, acknowledged and kept in the buffer, data which has arrived and kept in the buffer but not yet acknowledged, and data which has not yet been received. From the sender's perspective, these four states may happen. It has sent some data and it has been properly acknowledged. So it is clear that that amount of data has been clearly received at the other end. Now it may happen that it has sent some data and it has not yet been acknowledged. So it does not know what is the current status of it. It may be in the pipeline, it may in the other side buffer but not yet been acknowledged. So until and unless an acknowledgement arrives, the sender is never sure about the current situation of the data. So some data has been sent and acknowledged, that means that part of data has been correctly received. Some data has been sent but not yet acknowledged. Until and unless an acknowledgement is received from the user's sender's perspective, this data has not yet been received. Now there may be some data which is in its buffer, in its sender's buffer. They are in its window. That means it's ready to be sent but cannot be sent as of now, because it knows that if it sends this data, unless and until acknowledgement arrives for the previous data, it may happen that this data may create overflow in the receiver end. So some data are in its pipeline, in its window, but it is not yet been sent. Unless it receives some confirmation, we'll see how it is done. This data is only in its buffer. And there is some data which is not in its window. That means data is ready, but it is not in its current window. So unless and until the current window clears up, it cannot send this particular amount of data. Now let's see how this is actually implemented. How does the sender know how much data it has to send? Obviously, it will depend on the receiver's capability, how much buffer space it has, at what rate it is sending data to the application layer, but how the sender knows about it. Now let's see how it is done. Now we are saying that there is a buffer at the receiver end. Let's say two sides A and B are communicating. So A and B are communicating, and we are assuming that A is sending some data to B. So at the receiver end there is a buffer to store the incoming packets. Now let's denote the size of this buffer as RCV buffer. Let's use this term to denote the size of the buffer at the receiver end. Now the receiver will maintain two variables. One variable last byte read and one variable last byte received. What is last byte read? Last byte read is the number of last byte in the data stream read from the buffer by the application process. Now remember, we have already discussed that the bytes are numbered. When you are sending data, the bytes are sent as a stream of data. So they are numbered. We have already seen during our discussion of sequence numbers. So say we have around, say, 5000 bytes of data being sent from A to B. 5000 bytes of data are sent from A to B. Now remember, each byte is numbered. And how they are numbered, we have already said. Starting from a random number, they are numbered incrementally. Just for simplifying discussion, say these bytes are numbered from 0. So 5000 bytes, so there are total 5000 bytes, each bytes are numbered, so they are numbered from 0, 1, 2 up to 4999. So these are the number of bytes, and they are being sent inside different packets. So say 50 bytes in one packet, under 50 bytes in another packet, under 50 bytes in another packet, like that. Now last byte read indicates the number of the last byte in the data stream read from the buffer by the application process in B. What does it mean? Say there are 5000 bytes of data and A has already sent 2000 bytes of data. 2000 bytes of data. So starting from byte number 0 to byte number 1999, these bytes the sender side has already sent. Clear? So these packets arrive at the receiver's end, they are buffered, and time to time the buffer is cleared. Say up to byte number, and assume that all these bytes have been received correctly. So it has sent 2000 bytes and all these bytes have been received correctly. Say up to byte number 1000, from 0 to 1000, this number of bytes has been delivered to the application layer of the receiver's end. So data starts arriving from number 0. So up till byte number 2000, sender has sent, all bytes has been delivered to these receivers and they are first buffered, and in due time they are released to the application layer, and say the last number of byte that was sent to the application layer at the receiver set is 1000. So this number indicates the last byte read, the number of byte that was last read by the application layer at the receiver's end. And last byte received is the number of last byte in the data stream that has arrived from the network and has been placed in the receive buffer at B. So in this example, this would be byte number 2000. So the last number of byte that it has received, and it is in the buffer. It has not been sent to the application layer. So what has happened till now in this example? There are total 5000 bytes which are being sent from A to B. Till now it has sent from byte number 0 to 1999. Clear? Total 2000 bytes. From byte number 0 to 1000, it has delivered to the application layer. So 1000, the number of the last byte, which the number of last byte in this stream that has been sent to the application layer, this is the last byte read. So in this example, 1000 would be the last byte read. And from which number of bytes up till what number of bytes are there in the buffer? So starting from 1001 to 1999, this number of bytes are there in the buffer. They are not being sent to the application layer yet. So this last number 1999, this would be the last byte received in this example. This is a fairly simple example. So last byte read is the last number of byte that was sent to the application layer. Last byte received is the last number byte that has been received and placed in the receive buffer and not yet sent to the application layer. And some of the data are yet to be received from the other end. Clear? Now we have already seen that the size of this buffer is indicated by this RCP buffer. And we have already seen what is last byte received and what is last byte read. So there is some data in the buffer, some data already sent to the application layer, and there is some spare room. Now remember, the rate at which data is arriving from the other side, it should be such that this spare part is not overflown. That means data should come at a very specific rate so that this spare room is always there. This space is always available and no overflows take place. Now because we are not allowing overflow to happen, so this equation last byte received minus last byte read should be less than equal to receive buffer. This should be clear. So last byte received in that part, in the previous example, last byte received is 1999 and the last byte read is 1000. So this amount should always be less than or equal to receive buffer. Now this receiver side will maintain a variable known as receiver's window. Clear? So this receiver's window will denote what amount of spare space is available. Clear? What amount of spare space is available, this will be indicated in this variable. So this would be obvious. This particular expression would give the amount of space that is available. Receive buffer is the total size of this buffer minus last byte received minus last byte read. So this amount will give the spare room available in the receiver side. Now remember, obviously this particular value would be variable. It will not all fixed. Sometimes it may happen that this data is buffered up to this amount, so a very small amount is available. Sometimes it may happen that only a few packets are there, so almost the whole buffer is available. So this particular value will be dynamic. So the sending rate should also be dynamic depending on this rate, depending on this value. If there is more space available, it can send at a higher rate. If there is very small space available, the sender should send data at a much lower rate so that it does not overflow. But this we have calculated in the receiver side. The receiver side is calculated at its end. But how does the sender know about it? Obviously, the sender should know about how much spare space is available. Only then it can send data at this particular rate. This is done by using this header field receive window. Every time a packet arrives from the sender, and when the packets are stored at the receiver's buffer, the receiver calculates the value, receiver's window size, and whatever value it gets, it will insert in this field, and whenever it sends the acknowledgement, this value will be updated and sent to the sender side. So when the sender receives the acknowledgement, it looks at this value and understands that how much space is available at the other end and at what rate now it should send data. Clear? So look at this whole process. The receiver calculates the amount of space available in its buffer, and this amount of space is indicated using this header field known as receive window. In this receive window, we'll simply insert the amount it has calculated, whatever amount of space, spare space it has got in its availability, and then it will send this acknowledgement to the other end. When the other end receives the acknowledgement, it will see what amount of space is currently available, and it will send data at that particular rate so that that spare space is maintained correctly, then that there is no overflow. So then how the sender is informed, host B, the receiver, will calculate how much spare room is available and then will place the current value in this particular header field. The current value of RW and the receiver's window in the receive window field in every segment it sends to A. In acknowledgement or in any regular segment, you will insert this value. Remember, initially the value will be the full size of the buffer. At the very beginning, obviously the buffer is empty, so at the beginning the receiver window size will be equal to the size of the receive buffer. Clear? Now what happens at the sender side? How does the sender maintain what variables is maintained? So the sender maintains two variables, last byte sent and last byte acknowledged. There are two variables, last byte sent and last byte acknowledgement. So last byte sent is the last number of byte it has sent. In the previous example, what is the last number of byte it has sent? The last number of byte it was sent was 1999. Remember, we have assumed that it has sent 2000 byte. Clear? So 1999 bytes was the last byte sent in that example, and last byte acknowledged is the number of byte that has been acknowledged. So if the from the other end it has sent an acknowledgement up till byte number say 1800, that means this is the last number of byte that has been acknowledged. Clear? So what does last byte sent minus last byte acknowledged gives? Can you think for a moment? What does last byte sent and the difference with the last byte acknowledged? What does this give? This gives the amount of unacknowledged data A has sent into the connection. Now remember, this data may have arrived at the other end and kept in the buffer but not yet acknowledged. It may happen also that this data is in the pipeline, in the transmission link, it has not arrived at the other end. But from the sender's perspective, it is the data it has sent and has not yet been acknowledged. But how does it use this particular information? What it does is that it ensures that the amount of unacknowledged data, this amount of acknowledged data should be less than the value of receiver's window it has received from the other end. That means last byte sent minus last byte acknowledged should always be less than or equal to the receiver's window value it has received from the other end. If this exceeds this value, then obviously there will be overflow at the other end. Clear? So this should be very simple to understand. So by using this technique, TCP achieves this aspect known as flow control. So it ensures that the sender sends data at this rate at which the receiver's application can process data. And how does it achieve? By the receiver calculating the amount of spare space and then informing that amount of spare space to the sender, and that sender using that information and regulating its data sending rate. Clear? This is how TCP flow control works. Now there is a very small issue here. It may happen that the buffer at the receiver end becomes full. It may happen. And when the buffer space becomes full, obviously the value of receiver's window value will become 0. Clear? So whenever it now sends an acknowledgement to the other side, what it will do in the receiver's window header field, it will simply insert the value 0 and send to the other side. When the sender receives this particular packet, it sees that there is no spare space available. That means it now understands that it should not send any more packet. If any more packet is sent at this moment, it will become useless because there is no space available in the receiver's buffer space. So obviously it should not send any packet. Now then, how does the sender know that when to send next packet? How does it know that the space is clearing up? Remember, the receiver only acknowledges, and when it acknowledges, then only it informs about its current available space. It will not on its own send this current available space information to the sender. That means whenever sender is sending some data packet to the receiver end, then only receiver will store that packet in the buffer, and then in the acknowledgement it will send information that this amount of space is next available. On its own, the receiver will not inform. So once it has informed that there is no space available, then how will the sender know when it becomes when space becomes available again? The receiver will not inform that space is now clear, start sending. This will not happen. Receiver will only send information when it receives a subsequent packet. But it is not getting a subsequent packet because the sender has stopped sending data, because it has already said that I do not have any spare space available. I have no spare space available, do not send any more data. So the sender stops. Without knowing, how does the sender will know that next when space opens up, when it should again send data again. So to solve this problem, what actually is done in TCP is that if the receiver says that I have no spare space available by setting the receiver's window value as 0, what does the sender do is that it keeps sending small packets, very small packets of 1 byte size to the other end. That means it continues to send data to the other end, small size packets of 1 byte each. Though it knows that there is no buffer space available, it continues to send small data packets which contains only 1 byte of data. These probe packets are sent so that it is informed when space becomes available again at the other end. So obviously after some amount of time the space starts clearing up. So when space starts clearing up, it will recalculate the value of receiver's window and the new value will be inserted in an acknowledgement, and when A receives that particular value, it understands that the space is now cleared up. Now it can send data in more amount. Clear? So this is how the TCP flow control works. So today we have discussed one important aspect of TCP, which is known as TCP flow control. So almost we have discussed all the header components of the TCP packets. We are left with discussing one important aspect of TCP, another important service known as congestion control. This we'll discuss in a subsequent lecture. Also, we'll discuss about how the timer value is calculated in TCP. These two aspects we will discuss subsequently in our further lectures. Thank you for today.